Hello viewers, my name is Dr. Saeed. In this video lecture, I'm going to present Adomian decomposition method for solving nonlinear partial differential equation. In the previous lecture, I did explain this very method, but for ordinary differential equations only. However, this wonderful method has potential to solve partial differential equation as well, especially nonlinear. And we know that nonlinear partial differential equations are not easy to solve, and we have very limited number of classical methods to deal with nonlinear PDEs. But we will see that this method, Adomian decomposition method, will solve almost all type of nonlinear PDEs and generates the solution in the form of an infinite series. Let's take a variable, unknown variable u, which depend on two variables. Let's call x and t. So x and t are the independent variables. Let's take our differential operator. Let's call it a, which apply on this variable u, and let's equal to some function h of x. We also assume that x and t both are positive. Let's take one initial conditions. Let's call it u, x at with some specific time, call it t naught, and let it equal to be some function, call it g of x, where h of x and g of x both are known function and both are continuous in their domain. Okay, we need to solve this differential equation, partial differential equation, and we need to find the value of u of xt. We need to find this unknown function. Okay, what we'll split this differential operator into various simpler differential operator. Let decompose this. This is why it has the name decomposition method. So we decompose it. Decompose it LT of u, where LT is the differential operator which consists only of independent variable with respect to t. If we have more than one terms in this partial differential equation which have derivative with respect to t, we'll take the one which have the higher derivative. Okay, then we will take Lx of u. This differential operator, as it's clear by its name, will contains those terms which have derivative with respect to x. And then we will collect all the terms which are non-linear, and we call it n of u, or any term which is free of any derivative, is equal to same with function h of x. So we decomposes the differential operator in three smaller differential operator which are linear in sense. Okay. Now we will separate the first LT of u and let it on the left hand side and put everything on right hand side. H of x minus Lx of u, and then minus n of u on the right hand side. Okay, we'll choose LT operator in the sense that its inverse exists. LT inverse exists, and we apply this inverse operator on both sides, which when apply on left hand side will cancel the LT, and we will left uxt on the left hand side. And when it applied on the right hand side, because it will be in the form of an definite integral, because L of t is a differential operator, so its inverse would definitely be an integral operator. So when we apply it on this function h of x, it will generate some constants. We also use this initial condition to get those constants. So when we apply here, it will have some different functions like h of x, some g of x, and some other functions. We call everything f of x, and then it apply on this term becomes L inverse of t into Lx of u, and then L inverse of t on n of u. Okay, here we need to decompose our unknown function which is u. So we decompose it in two ways. Let u xt be decomposed in the form of an infinite series from k0 to infinity uk xt, which I mean u0 xt plus u1 xt plus u2 xt plus so on. So we have decomposed the unknown function in the form of infinite series, and it has a lot of components u1, u0, u1, u2, and in the next we will find the values of these components and we will put the here, and it will in the form of infinite series with the solution of differential equation. Okay, we'll decompose u in this way, but we will take this non-linear term because it will be hard to deal. So we'll take the non-linear term nu and we will decompose it in a special way, again in the form of an infinite series from n0 to infinity an, where an are the Adomian polynomials, which are equal to an is equal to 1 over n factorial dn by d lambda n of this non-linear term and its summation from 0 to n lambda to the power I and ui xt, and at lambda is equal to 0 because we have introduced a parameter lambda, so we must eliminate it here. So these are special polynomials, call it Adomian polynomials. These are Adomian polynomials which can be found by using this formula. Okay, so we will decompose the non-linear term only with Adomian polynomials and the rest of the terms involving u with this infinite series. So in case if we have a linear partial differential equation where we will not have any non-linear term, so we do not need to have this Adomian polynomials. Adomian polynomials will only occur in case we have a non-linear partial differential equation. Okay, now we update our last equation, which becomes now uxt, which is in the form of infinite series. So this becomes summation k from 0 to infinity uk is equal to f of x will remain as it is minus L inverse of t L of x and u, which is summation k from 0 to infinity uk of xt, and then again L inverse of t and n of u, which is now summation n from 0 to infinity a n. Okay, now since our operators, differential operators, are all linear, so we can combine them. In the left hand side we change our dummy variable from k to n plus 1, and in the first tree in the right hand side we'll just replace k by n so that we have all the variables n. Okay, after this replacement, the left hand side I have k is equal to 0 since k is n plus 1, so it is n plus 1 is equal to 0 or n is equal to minus 1 all along to infinity. uk since k is now n plus 1, so it is n plus 1 of xt of course is equal to f of x minus L inverse t L of x, again summation which is now n from 0 to infinity un, and then L inverse t, and here since we have already dummy variable n, so we'll leave it as it is. Okay. Now on the left hand side we'll substitute one term out of this series. So when n is negative 1, it becomes u naught xt plus, again combine the rest of the terms from n 0 to infinity un plus 1 of xt, and the right hand side f of x and minus. I'm writing everything in the form of one infinite series because now they have the same starting variable, they have same index, so and operators are linear, so we can put in inside the series. So it is one series at the outside from n0 to infinity, and the inside we have L inverse t Lx of u n, and plus because we have taken n is outside, so it's now plus L inverse of t of a n. Okay, now we'll compare both sides, and after comparing, what we get is u naught x t equal f of x, and un plus 1 of xt will be equal to L inverse of t Lx of un minus L inverse of t of an, where n is from 0, 1, 2, 3, so on. We'll get this recurrence relation from the last term. Okay, we'll use this recurrence relation to retrieve all our components from starting from u naught, which will of course be given, and we'll take when n is equal to 0 in the next term, it generates u1, which will involve u naught, which we have already a value of x. Putting here, simplifying, we'll get u1, and the same way we get u2 and u3 and so on. And once we have all these components, we will not able to solve to get all those components. Of course, we will find few of them. U naught is already given, u1, u2 and u3. 3 of them are enough, so we'll get enough to get a series. Okay, once we have u naught, u1, u2 and u3, we'll plug back this in our assumed series here. So after using these components, our solution, which is u x t equal to, it is summation k from 0 to, okay, now if we take some finite number of terms like till u3, so n is capital N is equal to, in that case, u k x and t. So it will be approximate solution because we are holding n to be some finite number. In this case, maybe 3 or 4, whatever we are easily get these terms. It's very hard to get them manually. So if we use some software like Maple or MATLAB, so we can get more terms. But since this series is very fast convergent, so we need only few of them. So if we need approximate solution, we'll take few of them like n, and it will be approximate solution. But if we want to take the exact solution, in that case we must apply limit n from n to infinity, summation k from 0 to n, capital N, u, k and xt. Okay, in some cases the series will be of elementary one, the one we already know that, and it is possible in that case to sum the series and get the solution in exact form. So but sometimes the series will not be some specific series. We need to take few terms, and then in that case we have only the approximate solution. In both cases the solution is very fast convergent to the exact solution. Okay, now I'm going to just draw few Adomian polynomials just to make clear how they will be calculated when we have solved the example. Okay, since Adomian polynomials are n is equal to 1 over n factorial dn over d lambda n, and then we have non-linear term summation I from 0 to n and lambda to the power I and ui x t, and all that we have to evaluate that at lambda is equal to 0. Okay, when n is equal to 0, it becomes a naught 1 over 0 factorial, which is 1, d 0 by d lambda, it means it again have no meanings, and we have then n, and we have summation from I0 to n, which is 0. So I0 to 0, it means it has only one term, so which has I0, so lambda to the power 0 and u naught. So it becomes n of u naught. That means the first Adomian polynomial a naught will be equal to n of u naught. For n is equal to 1, a1, again 1 over 1 factorial is 1, and d by d lambda, non-linear term of summation I from 0 to n, which is now 1, lambda to the power I and ui at lambda is equal to 0. At lambda is equal to 0. Okay, it becomes d by d lambda n of, now I start from 1 and it will go till 1. So when I is equal to 0, it becomes lambda 0, which is 1. So it is u naught plus when I is 1, it is lambda time u1. at lambda is equal to 0. Okay, now we'll differentiate this term with respect to lambda. So this becomes n prime of u naught plus lambda time u1, and then we'll differentiate inside u naught. Since we are differentiating with respect to lambda, so u naught is free of lambda, it will be 0, and for second term we will get only u1 at lambda is equal to 0. And now plug lambda is equal to 0, and this becomes n prime of u naught, and this term will be 0, and in outside we have only u1. This is our a1. So it means a1 will be equal to n prime of u naught into u1. In the same way we can find a2, which will be n naught of u1 into u2 and plus 1 by 2 and double prime of u naught into u1 square. So you can check that if we take n is equal to and simplify plugging all these values, and you'll get this term. So you can have second Adomian polynomial where n of u will be given nonlinear term, and you can plug it here and you will have u naught, u1, and you can get a2 here. So in this way we can get few Adomian polynomials because we need them while we solve these reconciliations. So this is how we'll get the solution of our partial differential equation. In the next lecture I will take one example and I will apply this method to get this method clear. Thank you for watching.